So we now come to the first main result of this week's lectures, and this is the so-called Eurozone lemma. So the idea for Eurozone lemma is to separate closed disjoint sets using continuous functions, and I will describe what I mean by separating using continuous functions. But here just let me add that if you have a normal space, you can separate two disjoint closed sets using open sets containing them. So you have two open sets, open disjoint sets containing each of the two disjoint closed sets. And Eurozone lemma is trying to do the same thing, but rather using continuous functions. And before I come to the specific details of what I mean by separating using continuous functions, just let me add there's a remark that this theorem, the Eurizones lemma, is extremely useful to construct new continuous functions and it has applications within topology, in topology as well as in analysis. So if you for example, if you take a course in real analysis or measure theory, you will see that you need to sometimes approximate some discontinuous functions using continuous functions. So one of the applications is to approximate discontinuous functions using continuous functions. And this is used quite a lot in measure theory, for example, and also in functional analysis you use this kind of result. So so this Eurozone lemma is quite a, as I said before, it is a deep theorem. It is considered deep because, well, it has some very nice new ideas, and it proves that you can do this separation using continuous functions for normal spaces. And so now let me describe what I mean by separating disjoint closed sets using continuous functions. So let me give this as a definition. This is separation of disjoint closed sets using continuous functions. So what do I mean by this? So suppose that X is a topological space. So for the moment it is general topological space, may not be normal, and A and B are closed disjoint sets in X. Now we say that a continuous function f from X to a closed interval in R. So I'll take 0, 1, but it could be any closed interval a, b in R, but because each such closed interval a, b is homeomorphic to 0, 1, it is enough to work with this specific unit interval. So we say that this continuous function separates separates A and B if f restricted to A is identically equal to 1 and f restricted to B is identically equal to 0. So it is for each point f of A for each point in A is equal to 1 and f of B equals 0 for each point in B. So in this way we say that we are separating these two disjoint closed sets A and B using this continuous function f. Now notice that if, so this is a lemma. So if any two disjoint closed sets A and B in X can be separated by a continuous function. So there exists a continuous function like this f here, for which f of A equals 1 and f of B equals 0, then X is normal. So this is quite straightforward actually. So we just need to show that you have two open disjoint sets containing each of these closed sets. So let U be the inverse image of, let's say, 2 by 3 comma 1. Note that this set here is open in the subspace topology of 0 1, and so this is U is open, this is open and contains the set A. So since f inverse 1 contains A, we have that U contains A, right? So similarly we can take V to be f inverse. Now this time take 0 closed and 1 by 3, and again this is open in 0 1 in the subspace topology of 0 1, and so f being continuous. So I did not write what is f here. So of course here f, let me write it here. Let f from x to 0 1 separate A and B. So of course you cannot use the same function to separate any two pairs of disjoint closed sets. So this function f will depend on your choice of the disjoint closed sets A and B, and so given two disjoint closed sets, there may exist a particular function that separates it. So here we choose such a function and we construct open sets. So these are U and V are open because f is continuous, and V also contains B, and it is obvious that U and V are disjoint, and U intersection V is disjoint. So this means that X is normal. So we see that if you have this property of separation of disjoint closed sets using continuous functions for any given pair of disjoint closed sets, then X is normal. And basically the Eurizones lemma is the converse of this lemma. So Eurizones lemma is the converse statement. So this is that if x is normal, then any two disjoint closed subsets in X can be separated by a continuous function. So this is the statement of Eurizones lemma. Now let's try to visualize this using well, let's say we have two closed disjoint sets in R2. So suppose that you have one set here, A, B, and let's say you have another set here, let's say C, D. So now you want to construct a continuous function. So let us call this A and let us call this B. And you want to construct a continuous function which is identically equal to 1. So this is 1 and identically equal to 0. So 1 on A and 0 on B. So it's about trying to interpolate between the two values 0 and 1 and fill in the gaps between A and B, so to speak. So here, if you have just the real numbers, it is quite easy to do so. So if you have two such disjoint closed sets, you can take some kind of linear interpolation like this, and you will get a continuous function. So here also you can so on the left you can extend by 0, on the right you can extend by 1, right? So then you have a continuous function which is 1 on A and 0 on B. So this is 0 on B. So this is very easy for the real numbers R, and in general it is also very easy for metric spaces. So for metric spaces, Eurizones lemma is straightforward, and this is because if you have two disjoint closed sets, so let A be disjoint closed sets in a metric space XD, and then we can define the following function. So f of x, so for x in X, f of x is equal to the distance between x and A, and rather let me write x and B here, and divide it by the distance, the sum of distances between x and A and x and B. And I claim that this is a continuous function. F is continuous. F takes values between 0 and 1, and thirdly f restricted to A is 1, and f restricted to B is 0. So let's prove this quickly. First of all, it is clear that f takes values between 0 and 1, because it is enough to show that this is always greater than, so let me write it here. So dxa plus dxb is always greater than or equal to dxb. So this means that the function f is less than or equal to 1. So this is clear. On the other hand, this is fx is of course greater than or equal to 0, provided that fx is already greater than or equal to 0, because we have only positive values, right? So we just have to show that it is well defined, in fact. So it suffices, so let me write it in a new page. It suffices to show that this denominator dxa plus dxb is always strictly positive, and this also shows that f is continuous, right? Because it will be a quotient of two continuous functions, and the denominator is always strictly positive. So then f will be continuous. On the other hand, it is also easy to check the third part. This is because, if x belongs to a, then dxa is equal to 0, and this implies that f of x is equal to dxb by dxb, and this is equal to 1, provided we know that this is strictly positive. So this is strictly positive since x does not belong to B closure, which is the same as B, because B is closed. So we know that dxb, so using here that dxb is equal to 0 if and only if x belongs to the closure, right? So I can leave this as an exercise for you to show. This is quite easy. And so fx equals 1 if x belongs to a. So similarly, if fx belongs to b, then the numerator vanishes, and so f restricted to b is going to be 0. So we have this third condition as well. So the only thing that needs to be shown is f is continuous, and for this it suffices to show that the denominator is strictly positive, and this is again a same argument. So if x belongs to a, x does not belong to b, then this means that dxb is strictly positive. If x belongs to b, x does not belong to a, this means that dxa is strictly positive. And if x belongs to neither a and b, this means that both dxa and dxb are strictly positive. So in each of these three cases, we have that the sum is going to be strictly positive. So this implies that f is continuous, and we have separated our two sets a and b. So let me go back. We have a separation with respect to this continuous function f from x to 0, 1, separates a and b. So for metric spaces, this is not so difficult. What is required is to give a proof for Eurozone lemma for general normal spaces, and this is where the novelty lies. So let's try to see the statement and proof of Eurozone lemma for general normal spaces. So for the proof, we need the concept of what are called indicator functions. So what is an indicator function? So if you have a subset of a topological space X, the indicator function of A, we say that it is an indicator function of A, which is either denoted chi A or 1A, and this is defined simply as chi A of X is 1 if X belongs to A and 0 if X does not belong to A. So if you just see here, if you have some set, say this is A, then the indicator function is 1 for x in A, so this is 1 here, and 0 otherwise, so this is all 0. So this is the indicator function chi A. So we see that in general, and this is a remark, indicator functions are not continuous. Not continuous. However, indicator functions are extremely useful in analysis, and so the idea of Eurizones lemma can be used to approximate indicator functions using continuous functions. So for example, here there is a discontinuity at the boundary point. So let's say this is A and B, and there is a discontinuity of this indicator function at A as well as at B. So indicator functions are not continuous, and Eurizones lemma allows us to approximate indicator functions using continuous functions. Now we have another lemma which we shall need for the proof of Eurizones lemma, and this is lemma 3.2, and it says that x is normal if and only if for any closed set K in X and any open neighborhood, so open set U containing K, we have so there exists a continuous function. There exists a continuous function f from x to 0, 1 such that the indicator function of k and if you consider the indicator function of u, so this is the open neighborhood of k, then the continuous function lies between these two things for all x in X. So it's like a note that neither of these indicator functions for k or for u may not be continuous, but you have a continuous function that is sandwiched by these two things. So this is a very nice reformulation of normality, and you can use this separation. So given that you can separate functions in normal spaces, then you can get this criteria with indicator functions as well. So to illustrate this property, let's look at what's happening for the simplest case when you have the real numbers. So suppose you are given a closed set K, and you take any open neighborhood, let's say CD. So this is U, an open neighborhood U of K, and now you have two different indicator functions. So one is the indicator function for K, so this is chi K, which is 0 outside K, and the other one is the indicator function for U, which is 1 here. So this is 1 over a larger interval and 0 outside, right? And now we claim that there is a continuous function which is sandwiched between the two. So there is a continuous function which is something like this. So it is 0 here, then it is 0 here, and in between it is something like this. So this is the idea. So this is the function f, and you have here that f of x is less than or equal to the indicator function on u, and it is greater than or equal to the indicator function on k. So this is the idea for indicator functions, and note that and lemma 3.2 is actually is equivalent to Eurizones lemma. Eurizones lemma. This is because any two disjoint closed sets can be separated by a continuous function is equivalent to saying that any given any closed set K and any open neighborhood U of K, there exists a continuous function f such that you have this inequality for all x. So this part I leave as an exercise for you to check. This is quite easy, and we will actually show this lemma 3.2 to prove Eurizones lemma. So this is an equivalent statement, and we will prove this statement here.